Hello, and welcome back to Learning with Lee. In this episode, we're going to take a bit of a detour from the course we have been taking in order to discuss binary. I've been holding off on doing this because of the fact that it's not strictly necessary to understand how to program. However, in order to understand how memory works, how the different types that we've discussed already, such as ints and floats, are stored in memory, you're going to need to understand what binary is. However, before I take a look at binary and answer the question, what is binary, I'm going to take a look at the question of what is the decimal system that we use in everyday life and a few interesting quirks pertaining to it. For example, do we start our counting at 0 or do we start it at 1? You might think, looking at real life, you might go, okay, let's just add in a little fluffy cloud over here, add another fluffy cloud, and these horribly ugly and fluffy clouds happen to be, you might say, okay, there's one cloud, there's two clouds. So you're naturally going to say, I start at 1. However, do you start at 10 or 11 to add in a second digit? Or do you go to 100? Or, in this case here, would you go to 111? Before you add in a third digit? And the answer is that we add in a second digit at 10 and at 100. Suppose I have 13 divided by 10. I'm going to get 1 out, and I'm going to have a remainder. I'll just put the remainder over, sort of up here, at 3. And let's suppose I have 20 divided by 10, because this is where we're going to go into 10 evenly. And for this one here, what I'm going to get out happens to be, this is going to go on over to 2 with a remainder of 0. And that sort of implies that we actually start at 0 for our counting, and we just ignore it in everyday life because it doesn't make sense to say that there's 0 clouds in the sky over here when there aren't any, and then, so let's say that in order to really drive this point home, how many numbers can you fit in before the digit 10, i.e. within a single digit, before you end up requiring a second digit to represent it using a decimal system? And that answer is 10 total numbers, because you can go 0, 1, 2, etc., all the way up through 9. What you wind up with is a total of 10. You might think, hang on, I'm stopping at 9, so clearly there's only 9, but the 0 adds an additional count there. So basically, each digit here means that you're going to have a total of 10 possibilities there. So your second digit ends up meaning that you actually have, and this could be a bit awkward, you actually have 100 possible numbers for it because of the fact that you start at 0 and you go to 99. Because otherwise, it would be really weird saying that you go from 1 to 100 to have 100 possible numbers, because then you're introducing a third digit for just the 100th of that set of numbers. Because otherwise you wind up with this weird sort of hybrid system in which it's like it's 2 digits for 99 of the numbers and 3 digits for one of the numbers, which is just really awkward. Whereas if you include 0, you get the full 100 in these 2 digits, and then once you add in a third digit, because you can go 0 to 999, you end up with a grand total of 1,000 possible digits in that area. And the way in which this can be further simplified, and it's considered in binaries, is that within your first 10, you're going to have 10 to the 1, because this is the number of digits that you have. So in this digit spot, because there's only one digit there, it's 10 to the 1, so 0 through 9. You add in a second digit, it becomes 10 squared, or 10 times 10, which is 100, which represents the 0 to 100. Well, 0 to 99. Then, as soon as you add this third digit, as you might be able to imagine, it becomes 10 cubed, or 10 to the 3, which ends up leaving you 1,000 digits, and so on and so forth. And this is very important to understand how much memory is available to you, how large your numbers can be represented in binary as well as in decimal, And it's part of the reason why it makes sense to start at 0. Because, as I said, otherwise you wind up with that weird hybrid system of it's mostly 2 digits to represent this set of numbers, but for that final one you need a third digit, which really is supposed to be a delineating factor in mathematics. So, the major difference between binary and decimal is that decimal, you create the second digit here once you have 10 numbers in your first digit over here. And in binary, you do that once you have 2 numbers in this first digit here. So you go, okay, I start out, and I know this still is going to be awkward for a while, but you start out at 0. And I'm prepending these zeros just to make it a bit clearer as to how this is. It's not really necessary, but it does help for clarity's sake. So I have that at 0. Then I go to 1. Now, because I have done 2 values in this first digit spot, I then go to effectively another digit. And now it's at 1, 0, which would be the equivalent of 2. Then I can keep counting and go to 3. And the way in which you then can understand what this is that really all that binary is it's a different counting system that is every 2 rather than every 10 for when we add in new digits. So you might be wondering, okay, well, how do you read binary then? Well, it has to deal with, you remember how I said that in this digit spot, it's effectively 10 to the 1, and in this spot here, it is effectively 10 to the 0, and while I didn't actually explicitly say 10 to the 0, it was somewhat implied by the fact that I did, okay, 10 is 10 to the 1, 100 is 10 squared, and so on and so forth. So the way in which this then is represented is over here, we've got 2 to the 0, we've got 2 to the 1, 2 to the 2, and so on and so forth over this way. So what you do then, in order to convert from binary over to decimal, is you multiply the value here by the value down here that corresponds to that number. So in this case here, we have 1 times 2 to the 1, so 1 times 2 to the 1 plus, and this all needs parentheses around it so that it occurs first in the order, and then 1 times 2 to the 0. And what that'll give us out is, on this side here, because 2 to the 1 is 2, gives us 2, plus, and 2 to the 0 becomes 1, so we wind up with 1. So we wind up with 3. And you can just do that for, even if, let's say that I had a 1 over in this digit as opposed to a 0. So then we would wind up with over here, we have 2 to the 3. And what that is, then, just multiply here, 1 times 2 to the 3, and then we'll just, for simplicity's sake, also toss in the fact that we have, and this is, well, plus, and then in parentheses, plus 0 times 2 to the 2, which this, of course, goes to 0. This, of course, over here ends up going, and it'll take a little bit to get used to it, but to 8. And then you wind up with 8 plus 3, and you get out 11. Since I've shown you how to convert from binary into decimal, I suppose the next logical step is how to convert from decimal into binary. The way in which you do that is actually fairly simple, and it can work from converting into really any other base. And that's this. Let's say that I have the number 1, 2, 3, or 123. Now, the way in which you would convert that into binary is, you go, okay, I need to divide this by 2. And what you'll get out of that is, you'll get 61 and a remainder of 1. So what you do with that remainder of 1 is you stick it in what is known as the least significant bit. If I redraw in my little thing of, okay, I've got 2 to the 0, I've got 2 to the 1, I've got 2 to the 2, and so on and so forth. The major thing then is that what I have is I go, okay, least significant is the smallest number up here. So in this case here, 2 to the 0, which becomes 1, and put the 1 there. Then I divide it again by 2, and I get 30 with a remainder of 1 that goes in the next least significant bit. I divide it again, get 15, which in this case here, because there's no remainder, or remainder of 0, we put in a 0 there. Go on down again, 7, add in a 1 there, divide, get 3 with a remainder of 1 there. And as you can guess, we're going to wind up with an additional pair of remainders of 1 here. And once this one here gets divided by 0, we have what's a quotient of 0. And at that point there, you stop. So the binary number you get out is this for converting 123 of 111111. And technically you can do the same thing for converting to other bases if you so want to. So let's say that I want to, for whatever reason, convert 123 into, let's say, base 4. So I do 123 divided by 4. So I end up with a quotient of 30, and I have a remainder of 3. I'm just going to stick that down there. I divide this by 4. The closest it comes is 7 times 4 is 28, and that has a remainder of 2. I divide this. 4 only goes into 7 once and has a quotient of 3. And at this point here, it becomes this. So this is converting 123 into base 4. So as you can see, it's a fairly general algorithm here, and in a couple lectures, I'll actually have you implement this as a bit of a homework assignment once we understand a bit more in terms of the things you can do in terms of flow control and loops and the like. But for now, what I'd like you to do is experiment around with the sum on your own in terms of converting different numbers into binary, converting from binary like this, and once again, if we're doing base 4, it just says, okay, here's 4 to the 0, 4 to the 1, 4 to the 2, and basically all you do is you multiply this number down here by this number here, and then you sum all of these up, and you wind up with the number in base 10. So I'd like you to experiment around some with converting between different bases like this, just so as you can get a feel for it. So there's one thing I haven't covered yet, and it is fairly important, and that is, why binary? Why not base 4 or base 3 or base 10 even? And it has to deal with some fundamental limitations of computers and how they're created and electricity. So to let you know sort of what binary is right now, you have a signal of 0 volts, i.e. no electricity traveling through it, and that's what represents a 0. And a 1 is represented by 1.6 volts, or thereabouts. It's a close enough approximation for this lecture. Then, let's imagine, okay, you could say, what if I wanted to have something at a few different intermediary levels, so as I could represent a higher bit number? Well, not higher bit number, but higher base. So, in this case here, we would have base 5, because you could have 0, 1, 2, 3, 4, 5. And the problem with that is what is known as background radiation. It comes from the sun, it comes from other natural events, but basically what happens is that when some solar radiation comes on in, hits down in here, what's going to do is it's going to cause a spike in energy and a spike in electricity on that particular wire or the like. And all of a sudden, you're going to have this false signal of where it was supposed to be 0, it's now showing up as 1 or 2. And that's a huge problem, because now you no longer know how your program is actually going to behave and run. Because you're getting these false signals, you're getting a whole bunch of noise at pretty much every single level. So what engineers did was they basically said, okay, we're just going to cut out any of these middle layers. We're going to choose 2 different voltages that happen to be so far apart that it's unlikely that there's going to be a spike strong enough to actually cause a false signal. So you still get spikes, but it's a matter of, is it below 1.6 volts? Then it still counts as 0 volts effectively, and is a 0. Is it above 1.6 volts? Then it's a 1. So that happens to be the general reason for why we actually chose the binary system over any other base that we could have chosen. And with that, I'm going to wish you all a wonderful day. I will see you guys next time.